In this quick video, I will implement a convolutional neural network on the very famous MNIST dataset and achieve a score of 99.7% with TensorFlow. Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So here I'm looking at the Kaggle competition page of this dataset, and if you go to the data tab, you will see the two files that we have to work with. The first one is train.csv, and that has 785 columns. That actually represent the whole MNIST dataset. So the MNIST dataset is 28 by 28, so that will give you 784 columns. And another one is because the first column is labels, that is we have total 10 labels. And if you go to the test.csv, there is no label column, so the very first column itself starts with pixel. So that's how in the test.csv I have 784 columns. And now I'm in my VS Code. I have downloaded all the data in my local machine. Initially, all the regular imports, all the keras layers, and from the scikit-learn I am importing train test split because I need to split the training data. And then just read all the regular step. Actually, read CSV will read the data in a pandas data frame, then check that you have the data frame properly brought into your notebook. So I'm doing head, so this is my data frame of my entire train.csv. First column is label, and then all the pixel starting from pixel 0 up to pixel 783, that is total 784 pixels, and the corresponding values. Similarly for test.head, and then because these data frame, that is these pixel values, are not actually normalized, that means the range of these values range between 0 to 255, so I have to normalize it. That's why I'm doing these two little steps to divide the values by 255, and then quickly check my shape. So my X train shape is 42,000 by 784, 42,000 because I have that many samples in my train data. Now I need to reshape it to a 4-dimensional tensor because I'm going to pass these data to the keras.image data generator, which will do the data generator job before my convolutional neural network. So before reshaping, just remember quickly that in TensorFlow, the dimension of images for data generator is follows these kind of styles. That is, the first dimension is a batch size or the sample size in each batch, then height, width, and number of channels, which is slightly different from Pytorch, because in Pytorch the first dimension remains same, that is batch size, but then comes channel, then height, then width. And just a quick thing to remember when you are working with TensorFlow and Pytorch. So in this next cell, I'm just reshaping the previous NumPy array to this form. That is, first dimension I'm keeping at -1, that will be inferred, then my width, height, and number of channels. I'm doing the same for both train and test. But for Y train, I need a single vector where the number of classes should be 10 because it represents 10 different classes of MNIST. And then just print xtrain.shape, and now I got this 4-dimensional tensor. 42,000 is the number of number of samples in the whole training dataset. Width, height, channels. All right, now quickly plot a few of the images. And also note that I have to bring in two categorical to convert my Y train vector. It actually converts a class vector of integers to binary class matrix. That means a binary matrix representation of the input will be given as the output. And the reason that you want two categorical is due to how the relationship between your labels is understood by the algorithm. For example, suppose you made a color classifier, you mark red as 1, blue as 2, and orange as 3. Now you feed them into your neural network to help decide what your input matches. The math is going to say that orange is higher than red. That obviously isn't your intent, because That's now how it is. But the network will know that orange is greater than red just because the number it was given like that. And that's a problem that two categorical method solves. That is, it will convert your y vector containing 0, 1, 2, 3, 4, 5, 6 up to 10 to a binary representation of that vector. That is, for each of the target values, instead of so many numbers, it will only contain 0 and 1. And we can actually check that. Just print this y vector and print it. Yeah, so now we can see that each of the values of this y vector is 0 or 1. Now moving ahead, I'm in the next cell. I'm just plotting 30 images by running this loop for I in range 30 and then using plt.subplot. So these are my images from the MNIST dataset, and that's before applying any augmentation, because in the next step I'm going to apply a few augmentation on this dataset. So coming in the next cell, that's where I'm applying all these augmentation with the image data generator module. So this module will allow you quite a few augmentation technique to be applied on your dataset. So the first one I'm applying is rotation range 10, that it randomly rotate images through any degree between 0 and 360 by providing an integer value in the rotation range argument, and I'm providing the number 10 here. And also note, when the image is rotated, some pixels will move outside the image and leave an empty area that needs to be filled in. You can fill these in different ways, like a constant value or nearest pixel value, etc. This is specified in another argument called fill mode argument, which I am not specifying here. But the default value of the fill mode argument is nearest, which simply replaces the empty area with the nearest pixel value. Then the next augmentation, zoom range, it's obvious, it will randomly zoom some of the images, and the 0.10 actually mentions how much it will be zoomed. And then two more augmentation, width shift range and height shift range. And why we need to apply these two shift augmentation on the images is because it may happen that the object in the image may not always be in the center of the image. To overcome this problem, we can shift the pixels of the image either horizontally or vertically. And this is done by adding certain constant value to all the pixels. And so we have these width shift range and the height shift range to apply the horizontal shift and the vertical shift in images. If these value is a float number, that is, I am providing actually a float number of 0.1. So if this value is a float number, that means it would indicate the percentage of width or height of the image to shift. Otherwise, if it is an integer value, then simply the width or height are shifted by those many pixel values. And now coming to this commented out code part, I was just experimenting with few more augmentation. For example, this brightness range, this accepts a list of two float values and picks a brightness shift value from that range. Values less than 1 darkens the image, and values higher than 1 brightens the image. But I ultimately had to decide not to bring in this brightness range, because my overall accuracy from the model was deteriorating when I was doing this augmentation. And another very common augmentation is horizontal flip and vertical flip. This again is more applicable for symmetric kind of images, like, say, example, you are predicting shape of football, where there are symmetries around the shape of the whole object. But in this case, in our case, MNIST dataset, these two augmentation will not improve your result, because you normally would not expect any of these MNIST images to be vertically flipped. And actually, when I was experimenting with this augmentation, my overall accuracy deteriorated. And now I also need to check the images after applying these all these augmentations. So let's come to our next operation. So remember, here in my X train, each row represent one single image, and if I print the row shape, for example, I'm just printing the 25th index number row, and that would give you this kind of output, that is 28 by 28 and 1. This last one represent the number of channels. And so in the next cell, I'm just printing the 25th row, and that gives me 3. And if I comment that out, let's say I am printing 11th index number row, and if I run it, I am getting the number 9. Similarly, let's print 18th index number row, and that would give me number 7. So now in the next step, I am just going to take these 25, 11 and 18 and plot them to see how they look. So in this cell, that's exactly what I'm doing. I'm running a loop with a range of 30. So each row I will be printing or plotting 10 images. For my first row, I am randomly selecting this 25th rows, and here remember this 25th comma, that means this array will select all the columns but only the row numbered in whose index number is 25. So in this loop, I am just printing these plotting this x train random for the very first row, but for the second row, that is while running the loop, for my second row, that is which starts, the index number will start from 9, I am printing the different image which is index number 11. And for the third row, whose index number will start from 19, that is because I'm running this loop in 30. So and each row I am printing or plotting 10 number of images. So 0, 9, 19, that's the kind of that's why I'm choosing this kind of loop here. So for the third row, I'm just plotting these 18th index number images, and if you run this, I'm getting this this plot. So this, remember, after applying my augmentation. All right, with that, I am ready to build the model, and for model selection, I'm going to take the very good old LeNet5. So this is the very famous original architecture of LeNet5. I am going to make, so I'm going to follow these layers, but for the filter size and for my activation function, I'm going to do some little changes, and we'll see that in a second. So here in this cell, my build model method is what's implementing this LeNet5. Now see one very particular way that this method is constructed. So this whole loop that you see in here, that's actually one single LeNet5 architecture implemented. But this whole thing I'm repeating so many times, and how many times, that's decided by these argument number of CNN, num-CNN. So initially I have this model variable declared with this line, and then I'm looping through these num-CNN, that is for j in range num-CNN, and for each j value I am adding these entire LeNet5 architecture to my model. So whatever is a num-CNN, that many number of CNNs or that many number of LeNet5 actually will be added to this model. So for the final output or the final submission, that will be an ensemble of all these different models. And as to the details of these LeNet5 architecture implementation here, only few modification which are kernel size. So instead of 5 by 5, I'm choosing 3 by 3 filters. And for the, I'm also adding this batch normalization, and the activation I am bringing in ReLU instead of sigmoid. And the final thing is strides. So I am including strides too, which replaces the pooling layer. And then otherwise, this architecture is just adding one layer on top of another, following LeNet5 flow of architecture. And in the final layer, I am just final line, I'm just compiling this whole model, and the optimizer choosing Adam, loss, categorical cross entropy, matrix accuracy, and returning this model from these from this method. Now this model returned from this method will be invoked many times for each epoch, and that's what I am doing in the next layer. So in the next cell, I'm just deciding this number of CNN to be 10, and that is this whole model, this whole build model will be running this entire architecture for 10 times. So now in my train pipeline, I need to implement this model for 10 number of CNN, and that's what I'm doing here in this next cell, the train method. So first I'm just declaring my learning rate scheduler, which will continue reducing the learning rate throughout the epochs by this lambda function. And then I'm declaring the history variable, and then for CNN in range num CNN, that's where I'm starting the loop. First thing I'm doing, I'm splitting the data set. 90%, that is test side is only 0.1, that is 10% test, 90% train. And then the history variable for this CNN will have the model CNN.fit. So this whole thing will run for 10 number of CNN. And for each of the model.fit, how many epochs? That is decided by this num epochs, which is an argument to this train method. And later in the next step, when we will implement this train method, we will see that num epochs I'm defining 45. So this model.fit will run for 45 epochs, and then these entire model, that is this entire 45 epochs, will run for 10 number of times. And that's what making these whole architecture so powerful in getting my high accuracy. So let's do that. Now, before running the actual training, note one thing, that the total, because of the special architecture, that is 45 epochs for each model.fit, and total number of model.fit will run for 10 number of times. So total how many images, or how many total number of image count I have, and that's 17 million. How I'm getting that? Just this multiplication. So you have 42,000 number of sample image. To that you multiply 90% of this 42,000 I'm training as my train split. That you multiplied by 45 epochs, and again multiplied by 15 CNN, or actually this is 10 CNN. So that will give you 17 million. So that many number of images the whole training is actually working on. And I was actually running these entire notebook in a separate notebook here in my Colab, and the kind of output that I was getting when the epochs was continuing is like this. So my validation accuracy for the very first CNN was giving me 99.643. Then so this is the kind of way it was progressing, 99.8, 99.595 similarly. So after running for all the 10 CNN, I have to ensemble the final prediction from all the 10 CNN. So let's do that. But before that, quickly check. I have to do some reshaping here before the final ensembling. So my x.test dataset is shaped like this, 28,000 by 28 by 28 by 1. I remember this is my test dataset, not my train, and we had 28,000 number of images in the X test. And then I have to reshape the final vector to be to have 10 different target values, and that's what I'm doing in this line, final ensemble prediction np.0. So I'm initiating with np.zeros. And the first dimension will obviously take this 28,000, because that many samples, and a second dimension, that is number of columns, will be 10. And if I print, that's what exactly I'm getting, 28,000 by 10. And then for the final ensemble, this is a code here. Practically I'm just generating a data frame to contain my ensembled prediction from the 10 CNN. So here in this cell, all I'm doing is I'm adding the prediction from all the 10 different number of CNN, and then from that summation, I am taking the argmax here. And to implement that, I just have to run this loop, that is j in range num CNN. and for each index number, that is each j number, I am doing model j dot predict. That will give me the prediction for that particular CNN number, and passing x test. Then in the next cell, I am just doing this np.argmax to get my maximum value from this summation. Finally, in this line, I'm just converting this numpy array into a pandas data frame, and then in the last line, concatenating all of them and converting to a CSV file for submission to Kaggle. And with this ensembled submission, the final accuracy score I was getting from Kaggle is around 99.7%. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with Pytorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.